Okay, I'm going to give you guys a tool early. There's a thing called separation of variables. Okay? My claim is you've actually been doing something kind of like this anyway, but I'm going to do just a quick, easy example. So let's say I had y prime is y. Oh, what the heck. Let me put a k in here just for kicks. The k stands for kicks. Okay, so where have we seen this before?
Yesterday.
Yesterday. Yeah, I'm down with yesterday. That's good with me. So yesterday we saw this, right? Yesterclass. Yeah. So this was a population model, right? So how did we solve this? Yeah, we totally just guessed and fiddled around for a little bit, right? So I claim that you can use calculus to solve this, but you have to be a little bit fast and loose with the idea of calculus. Okay? So it should be noted that separation of variables is a silly, silly trick that happens to work. Okay? Okay. So I'm going to pretend that I know absolutely nothing about these symbols. I'm just going to write them down. Y prime is dy dx, right? And this is ky. Okay, now I told you that you're supposed to solve for y, right? Yeah, I'm going to do the dumbest possible thing. I'm going to get the y's to one side and the other stuff to the other side. Right? So I'm going to write this out like an algebra lecture just because I want to be totally clear that what I'm doing is total nonsense, but again, happens to work. So what are you going to, how do you, wait, what? What do you do? Tell me.
Multiply by dx?
Yeah. Multiply both sides by dx. Right? No thinking. There's no thinking when you separate variables, okay? Just stop. So you get dy is ky dx. Right? And then you divide by y. Don't divide by I said no thinking, not abs. You said no thinking. I know. So divide by d would be a good step, but would be would not be separation of variables. Thank you for highlighting that. The d and the y are stuck together. I don't know why. Believe it or not, I don't think anyone has ever said that before. Like, I'd give this same lecture in that same way. Like, you just turn off your brain and you do this stuff. Thank you. So, I think I want to divide by y. So I'm going to multiply through by 1 over y. So I'm going to get 1 over y dy is k dx. Okay, we have to think just a little bit harder. I'm sorry.
Something good required. You just derive y, right?
No. Then we're going to slap a squiggle on both sides.
Integrate.
No, actually we're going to multiply both sides by a squiggle.
We're going to d both sides.
We're going to d both sides. So we're going to get the integral of 1 over y dy is the integral of k dx. Cool?
Yeah.
Okay. What's the integral of 1 over y?
The natural log y?
Natural log y seems legit. And on that side you're getting kx.
Do we need constant?
Yeah, they need a constant somewhere, right? My advice would be to stick it on the side of dx.
Wouldn't you add one on both sides? Are you doing an integral on both sides, or is that
Yeah.
just assuming you're
One they can combine.
Yeah, so you could do plus c1 on this side, plus c2 on that side. Subtract c1 from both sides. That would get you to c2 minus c1, and then you might call that constant c. Cool?
Kx plus c.
Okay, now you need y, right? You don't want to know about log y, you want to know about y. So now you slap a log eater on both sides. Right, so you stick an e under both sides. So you do e to this stuff, right?
Yeah,
So you get y equals e to the kx plus c. All the kx plus c is where? Yeah, all that jazz is in the exponent, right?
Can you eliminate the absolute value slot or no?
Yeah, I totally forgot the absolute values, right? You guys all see that? Really, we probably should have had some like log of the absolute value of y. So we should have like the absolute value of y here, which really amounts to a plus or minus y.
And then you define the constant.
Yeah, and then we have to find our constant. You guys cool with us? So I think I end up with y is plus or minus e to the kx plus a constant. Okay, now use an exponent rule here. What can you rewrite that as? Yeah, you can rewrite that as multiplication by e to the c, right? So you got y is plus or minus e to the c, e to the kx.
And e to the c, can't that just become a c?
Yeah, e to the constant, right, is going to be a
Constant.
constant.
It has to be
With
positive too. Yeah, because he's constant.
So e to the constant is going to be positive, right? But you got your plus or minus here anyway,
Yeah.
right? So you really end up with y is p0 e to the kx. Right, where p0 is some arbitrary constant. Specifically, that arbitrary constant is what you get when you plug 0 in for x, right? Which is why I'm thinking about it as population at time 0, right? You guys
But if
with
we
me on that?
differentiated that,
You differentiate this.
we wouldn't get ky. Yeah, we would, sorry.
Cool.
Cool.
Good talk. So, I got here, right? Hey, that's kind of cool. Like, that seems to be the solution that I arrived at yesterday by guessing. Okay, so do you guys want to see the real deal for separation of variables and not the stupid trick?
Sure.
Okay, so let me back up a stage here. So this is, by the way I would actually encourage you to do separation of variables. Multiply through by the dx, and then integrate both sides. Get all the y's to one side and all the x's to the other. It doesn't always work. So not every equation you're going to be able to do this with, but a lot of them you can. Does that make sense?
How would you know? It would just be.
Try it.
If it had an x in on the right, it would be impossible.
No, we could probably do it with an x on the right. It's a question of whether or not you have y prime equals some function of x times some function of y, right? Like, if you can solve that thing in such a way that all the y's end up on one side and all the x's end up on the other, you're at least set up okay to try. That's still no guarantee that you can actually integrate both sides, right? Like, some of those things you'll be able to integrate, some you won't. It doesn't always work, but it's a nice thing to try because it's fast. Like, separation of variables is a quick thing to try. So let me maybe just say at least what's quickly going on here. So quickly what you're doing is you're saying, okay, I'm going to multiply by 1 over y. That's a legit step you can do with equations, right? So you have here 1 over y times dy dx equals some constant k, right?
Why can't be 0 then?
Y can't be 0. Yeah, y can't be 0 in this case. That's true. We could see that from the form of it that we got at the end. Okay, and then I could integrate both sides with respect to x. Like, that's actually a step I can accomplish. If I integrate both sides with respect to x, I'm playing a fair game. You guys see that? Like, that's not some BS step. This nonsense is a function of x, right? because y is a function of x and dy dx is still a function of x. So I can definitely at least put the idea of antiderivative on that side. So I'm going to integrate both sides. And this is not some BS about slap a d-eater on there. This is actually calculate the antiderivative function for both sides with respect to x. So I'm getting the integral of 1 over y times dy dx with respect to x. And apparently that ought to be the antiderivative of k with respect to x. You guys all see that?
Yeah.
This is okay. This part I can integrate. Right? Like, you know how to integrate k with respect to x. What's the antiderivative there?
KX.
Yeah, just kx, right? Oh, I erased the thing I was going to get. So I get k times x plus a constant on that side. On the other side, I still have the integral of 1 over y dy dx with respect to x. Which feels like you're totally stuck, right?
Feels like about 3.
Can't we just cross out the dx's if you did the last one?
Yeah, so crossing off the dx's is something I don't have any mathematical justification for, right? Because those things are they're not fractions, right? So even though they play like fractions in the chain rule, they're not actually fractions.
Are we going to treat y as a constant right here, or we're
No.
not? That's not the same thing?
No, y is definitely a function of x, and it better be.
Okay, I just didn't know if we were going to integrate and then treat y as a constant, like,
No,
okay.
no, I'm not pulling a bullshit trick on you here.
Awesome.
So the trick that I'm going to pull, which is not bullshit, is I'm going to do u substitution here. You guys see that? The u substitution I'm going to do is I'm going to say let u be y. Then what's du?
dy. dy du?
So the way you do u substitution, right, is you say, okay, du is the derivative of u d whatever that thing was, right?
It's right there. It's a function.
So it should be dy dx dx. You guys remember this trick? And where's my u up there?
On the denominator?
That's all of this stuff. That stuff is du.
So normally though, if we were doing this in Calc 2, we would say that it would just be dx, right? Because the derivative of, if it was like x.
If it was x, then the derivative, right, of x is 1, and then you put the dx on there because it's a differential.
How'd you get the extra dx dx though? Because I thought it would
This
be
guy?
d equals dy because if the differentiate both sides, the derivative is d.
Okay, so let me try another example. Say I had the integral of, oh, I forget which one this is. It's either cotangent or tangent. Cosine over sine is tangent? Cotangent. They both work the same way, right? To calculate the antiderivative, what do? Do u substitution, right?
Yeah.
So you let u be sine of x. Then what's d? It's cosine of x dx, right? How did you get that?
d dx.
You took this part, differentiated it, and then you wrote dx afterwards.
Yeah, but there you didn't write over dy times dy. Like, where is the over dx dx stay there? Why is
So,
it just dy?
This guy, right, is d dx of that thing, and then there's a dx. So the thing I had there was y, and I put a d dx on it, and then I put a dx after it. You guys see that? And the justification for doing that was the chain rule in the first place. You guys remember that?
Yeah.
Okay, and now, if I notice what I've got here, that guy, after u substitution, is the integral of 1 over u du. Right? Which is what we ended up with, except we had y equals u. You guys see that? But y does equal u, because that's the u substitution I made. You guys see that? Basically, this amounts to the chain rule actually does let you cancel those dx's. Cool? It's there. It's all the way at the bottom of the chain rule. Cool? So even though substitution of variables looks like this dirty trick you're pulling, because you're going to multiply both sides by a dx and then slap an integral on the sides, it is actually legitimately just the chain rule played out over again.
It's just kind of easier to think of it.
It's much easier to think of it the other way because you don't have to go through this trick that I was, like, Seven and I are going back and forth on, right? And he's got a reasonable point, right? I'm playing a little bit, like, this is a little bit wobbly and it's a little funny looking, right? Which is why I want you to just do it the dumb way because it's easier to get it right.
I just wasn't seeing the chain rule in there, but now I see it.
Yeah, no worries. And, like, I know you see it now. I just don't want you to have to go through and see it every time. I just want you to do the dumb thing. Cool? All right. So what I want from you guys is to do 8, 9, and 10 in 1.2. So add that to your homework list.